Hi, in recent videos, we have gone over two important topologies designed around MOSFET. In the first, we had connected voltage source on both input and output sides. Keeping the input side same, we connected current source at the output side instead of voltage source in second circuit. In the first case, as output voltage was constant to VDS, we observed change in IDS. In the second case, we got change in output voltage VDS as we had a fixed current IDS. There is one important consideration I want you to remember before going ahead in this video. That will be keeping VGS constant for all circuits is what we are going to do in this video. Small signal current of Gm times delta VGS is what we got flowing from drain to source in first case, which you are seeing on the left. And small signal voltage translation of Gm times delta Rout times delta VGS is what we got in the second case, which you are seeing on the right. If product of Gm and Rout, which are by the way parameters solely decided by MOSFET, comes out to be greater than 1, then we have achieved voltage amplification. It all started with goal of designing voltage amplifier. As just discussed, we already got a configuration where we get voltage gain, just so that the parameters which decide gain are not in our hands. Well, we can change Gm and Rout both at the same time by changing the region of operation. Let's look at one more method where we will have at least one parameter which sets gain totally in our hands. Let's see how we can do that. From the second circuit, we know that we have to get control on either of value, which is Gm and Rout, or both, so that we can at least control the gain of MOSFET without hampering the operating region of MOSFET much. Why we don't want to hamper operating region of MOS? Well, let's see that first. We know that we need some amount of Gm to achieve gain. As seen here in the Ids-Vds graph, definitely we don't want to work in the region shown by green circle, which we also know that it is a cutoff region. Around the region where VGS is nearly equal to VTH, we see that Gm starts rising. Gm is maximum in saturation region. Let's look at Rout now, which we get from Ids-Vds plot. We can see that Rout is maximum in saturation region. This is great. Gm and Rout both are maximum in saturation region. So we can bias MOS in saturation and we will get maximum gain for the circuit we are analyzing. Let's have a look at the small signal model, especially at the output side, as we will get gain from there. We saw that small signal current Gm times delta VGS flows through Rout and thus gives gain of Gm times Rout. Current has no other way to go, that's why it is going through Rout. Well, let's give it one more path to flow. What if we connect a resistor externally between drain and source? Now current has two paths. First cut intuition is, if we set value of R much less compared to the value of Rout, most of the current will flow through R and small part of the current will flow through Rout, just because R offers less resistance than Rout. Let's see that how current will divide. Let's take simple circuit with two parallel resistors. By doing fairly simple calculation, we can get to expression of current split. We can also imagine combination of two resistors as a single resistor of value which you can calculate by formula you are seeing right now. Pause here if you want to stare on this some more. Now let's get back to our circuit. Replacing two resistors with their equivalent one resistor, we will get the gain of Gm times R total, where R total can be found using the equation we just saw. Notice that we are trading our absolute value of gain with having control over the gain. How? Let's say that we had Rout of 100 kilo ohms. Any resistor you put parallel with Rout will take some current from Rout. This sure will reduce your gain. So keeping the value of Gm constant for our analysis, maximum gain you can get is only when you don't put any external resistance at the output. This Gm times Rout gain is also called as intrinsic gain of MOS. Advantage you get when you put R is control over gain, because now you can change the value of R and change the gain. This is the trade-off we have to deal with. As of now, we cannot say that operating point will change based on addition of R, because we have only analyzed small signal circuit, but operating region is set while biasing. We haven't thought of biasing yet, let's see to that first. Let's pull up our friend Ids-Vds plot and see what we get out of it. Let's first construct a circuit with inclusion of R. Now, this was our original circuit. We will now add external resistance from drain to source. Done. This is what our final circuit looks like. Let's get to Ids-Vds plot now. What you see here is a single trace from Ids-Vds graph. In absence of R, full current of ID will flow through MOS, which will generate VDS across it. One thing to remember, Absence of R can also be said as presence of R of value infinity. So what we analyzed was when R equals ideally infinity or practically much higher than R out. Let's reduce the value of R and see what it translates to. As value of R reduces, ID current gets another path and R starts to take some part of ID. Hence current going through MOS reduces. This current split will be based on the values of R and R on. Why R on and not R out? Because we are not analyzing any small signal property here. Can we somehow visualize this current in graph? We just said that current through MOS will reduce as we decrease value of R. Hence the operating point, which was the red dot shown, will not be the same and will start moving somewhere left on the same trace of VGS. As a result of this, we can see that the value of VDS will also reduce because the reduction of IDS. This is an important observation. But there is one more guy who is demanding the value of VDS, which is the resistance R. The current which started flowing through R will generate voltage across it. Thus we can see that VDS is not only determined by MOS but also by R. This means there is a fight happening on value of VDS. Let's see when it will settle. As indicated on the y-axis, IDS is the current flowing through MOS. Hence ID minus IDS current will start flowing through the resistor. This current can be indicated as the remaining part of the current ID on the same y-axis. As the MOS current rises, external R current will reduce and vice versa. You can see that we can embed one more graph in here with the origin at the green point you are seeing here. The graph will be of the current through resistor versus VDS. The cross lines you are seeing are the plots corresponding to our new plot. If you wrap your brain around this enough, you can easily see that as the current through R increases, the required voltage across the resistor increases. Thus the points of intersection of red trace and green trace will be the steady state for this circuit, which are indicated by blue points. This is just amazing. Different green traces are for different values of R, and as you can see, there is a range of values of R for which the MOS will be in saturation region. Thus, in this way, we got to know that the value of R affects the operating region of MOSFET. We were not sure about this sometime back, but now we know that it affects. Let's take a recap. So we know that small signal gain will be Gm times R out parallel R. We wanted the value of R much less than R out so that our gain will be almost equal to Gm times R. And this gain can be controlled by varying value of R. This requires that we keep MOS in the saturation region so that Gm won't change. But now we saw that change in value of R affects the operating point of MOS, and certain range of values can only be used for R to keep MOSFET in saturation region. This is the exact trade-off we have to deal with. If you are new to this, you might get a feeling that why did we complicate this graph by embedding one more graph in it? Well, because it will help me in explaining very important point which I am about to tell you, which I think you will appreciate it too. In fact, you can think that this is the main takeaway from this video. Let's take the circuit with no R connected. In that circuit, we were having external current source of value ID which used to set the initial operating point. This also used to determine the value of VDS. Well, we can try the other way around now. Let's set the current through MOS by setting fixed VDS. This is the first circuit we saw when we started this video. What you see here is a circuit with forced VDS voltage. We know that we should put R across R out in small signal model to get control over the gain. But if we put resistor across VDS here, there will be no effect on the circuit. This is because the current through MOS is not getting altered by the addition of R. So this will not work. But if we put R in series with VDS, then we can change VDS seen by MOS by changing the value of R. For example, if R is 0, it's like normal circuit where VDS voltage is directly connected to the MOS. But if R is non-zero, current through MOS will first flow through resistor R and create drop across it. Thus, value of VDS for MOS is not equal to external voltage source. It is less than that because some of it got consumed across R. Pause and understand this as much as you can. Well, the value of current will also change, which we will try to find using the graph. Let's look at the graph Ids-Vds now. As seen, now Ids current is set by VDS. Similar to how we created that graph for voltage and current through resistor, we can create similar embedded plot here. Just that it will come on x-axis, not y-axis, because we are controlling voltage VDS here and not the current ID. Now where will the origin be on x-axis? It will be right on the value of VDS. We can draw a line for given value of R which will look like the green trace you are seeing in here. You might have noticed that similar to previously discussed case, there is a fight between which value of current this circuit will settle to. As seen, where both traces meet, there is this stable point of operation indicated with blue points at which the circuit will come to. Also, we will get different plots in the new graph for different values of R. Pause and see the graph carefully and you will be able to digest this easily. Similar to previous case, R will have range of values where operating point of MOSFET will lie in the saturation region. Now let me bring two graphs together. If you see, both graphs definitely look different, but eventually the trade happening is the exactly same. It's the fight of the final value of VDS or IDS which makes both of these graphs same. This is totally amazing. Moreover, we know that small signal models of both these circuits are exactly the same. This means the function that we get out of these two circuits is exactly the same. Just that the original control changes between current or voltage. Now I want to tell you the most important takeaway from this video. This somehow took me years to understand. We are saying that small signal analysis of both these circuits is exactly the same. If you see carefully, the R resistor is connected to the drain and source. Now in the first circuit, it is actually connected to the drain and source. So no issue here. But in the second circuit, it is not. It is connected between drain and voltage source. Time to pause again and understand this question. Our understanding from last videos is, in analyzing circuit using small signal model, we only consider time varying perturbations of voltage or current. We don't use constant DC voltage sources or constant current sources in small signal model. Similar to that, here we should remove VDS from the analysis in the case of second circuit. Now the drain has to be connected to the ground because only then the current will flow through R. It is just a coincidence that the source terminal also happens to be connected to ground. In this way, resistor R in the second circuit comes across the drain and source in the small signal analysis. Thus, particularly, DC current sources are removed from the circuit and DC voltage sources are shorted with a wire in small signal analysis. You might want to visit my last video for more clear understanding on why current sources are totally removed from the small signal analysis. Trick is to short constant voltage sources and remove constant current sources while analyzing small signal model. I would finally suggest that you go over my last video about understanding small signal analysis and then again this video so that you can get more comfortable with these thoughts. Because from now on, we won't be able to highlight these minor details about small signal analysis every time we see them. Rather, we can get intuitions from them which will help us solve these circuits. Thanks for watching.